Hi guys, welcome to my lesson on algebraic proofs. In this lesson, we're going to use algebra to write two-column proofs. I'm going to introduce this idea. We're going to define this and see what this means. And we're going to use properties of equality, things that we learned in Algebra 1, to first write algebraic proofs and then show that we can use that same idea to get into geometric proofs. What's really exciting about this lesson is here I get to dispel all the things that you've heard from friends and siblings who have taken geometry, that proofs are hard, proofs are the real hard part of geometry. And in this lesson, I get to show you that not only are they not that bad, but in fact, you already know how to do them, and you do proofs all the time without realizing it. Before we get into the lesson, let's look at our new vocabulary. An algebraic proof is a proof that consists of a series of algebraic statements. Okay, so what are algebraic statements? Well, essentially equations, right? And we're going to do some algebraic proofs using properties of equality that we already know, that we learned in Algebra 1. And then we're going to learn this idea of a two-column proof. And you'll sometimes hear this referred to as a formal proof. It's a proof that's organized into two columns. On the left, we have statements, and on the right, we have reasons. And we can make any statement we want as long as we can come up with something that we've already proven that justifies it as a reason in the reason column. All right, we're going to take a look at just a quick refresher of some of our algebraic properties before we do our first algebraic proof. Okay, here are properties of real numbers that we learned in Algebra 1. These properties are true for any real numbers, A, B, and C. And the first one we're going to look at is our addition property of equality. Okay, if A equals B, then we have an equation, right? Then A plus C equals B plus C. And this is basically saying you can take a true equation and add anything to the left side of it, as long as you also add it to the right side of it. Okay, that's our addition property of equality. When we first started learning how to solve equations in one variable, oftentimes we would add or subtract something from both sides. That was our addition property of equality that we were using. And our subtraction property of equality, which works the same way. If we have a true statement, if A equals B, then A minus C equals B minus C, because what we've done is we've subtracted the same quantity from both sides. Okay? And what I'm getting at here is that as we move on to doing proofs, we can use these as reasons, justifications for the work that we're doing, which is really what you're already doing when you solve equations. You're just not stopping to state it every time you do it. In the proof process, we're just going to take our time to state which properties we're using so that we're mindful of that. We also have our multiplication property of equality. If I have a true equation, A equals B, then I know that A times C equals B times C. I've just multiplied both sides by the same quantity. Division property of equality works the same way. If I have a true equation, if A equals B, and one stipulation here, C does not equal 0, then A divided by C equals B divided by C. And then we have our reflexive property of equality. Reflexive, think of this as when you're studying language, reflexive pronouns. Myself, himself, herself, things that refer to themselves are reflexive pronouns. And so A equals A, that's how you can remember that. A is referring to itself, A equals A. When do we use this in algebra? Not a lot. You don't use it a lot in algebra, but we're going to learn that there is a geometric equivalent. The reflexive property of congruence we're going to use all the time. It might look something like this. Angle A is congruent to angle A. Trust me, we'll use it a lot in geometric proofs. In algebra, you might not use it quite so much. Our symmetric property of equality, you use this all the time, you don't even realize it. When you solve and you find 5 equals y, but you like to write it as y equals 5, what did you do? you flipped it around. So if A equals B, then B equals A. Think of it as the symmetric property of equality. Draw a line of symmetry, and you can flip that equation over, and it's still the same thing. Okay, our transitive property of equality says that if A equals B and B equals C, then I should be able to conclude that A must equal C, right? And we're going to use this a lot, the transitive property of equality. We're also going to use the transitive property of congruence a lot when we get into our geometric proofs. And then we use our substitution property of equality. You probably use this more than any of the other properties of equality. You use this all the time and you don't even realize you're doing it. Here's what it says. If A equals B, then A may be replaced by B in any equation or expression. And anytime you simplify, anytime you combine like terms, you simplify an expression, you've basically been using substitution, right? If you've got 5x plus 2x on the left side of an equation and you replace it with 7x in your next step, well, you've basically used the substitution property of equality there. All right, and then lastly, we have our distributive property, which Algebra 1 last year, I always feel like this should have been the subtitle to that course, Algebra 1, the distributive property, right? Because that's pretty much what it was all about. If you distribute the A, if you have A times the quantity B plus C, that is equal to A times B plus A times C. All right, using all of these properties of equality, could we go ahead and do our first algebraic proof? Let's try it. All right, in this problem, they want us to solve the following equation and justify each step with properties of real numbers. So basically, this is saying they want us to do an algebraic proof. Okay. Now, when we get into our two-column proofs in geometry, we're going to have a column of statements and a column of reasons. In our algebraic proof, what we're going to do is we're going to call these, I mean, you could call them statements and reasons. They're essentially the same thing, but we're going to call these algebraic steps, okay, which are basically writing equations, right? And then our justification, our reasons for why we're doing what we're doing in these steps are going to be our algebraic properties, okay? The ones that we just reviewed, okay? And then you start every proof by restating the given information. The given information here is 2 times the quantity 5 minus 3a minus 4 times the quantity a plus 7 equals 92. Okay, and I'm just going to say that is our given information. Okay, now what would you do first here to solve this equation for a? And again, if I simply asked you guys to solve for a, I think you'd probably be fairly comfortable doing that. You'd take a few steps. Some people would take more steps than others, but I think you could work your way through it. If you started that, what's the first step you would take? I would start with a distributive property, okay? And I'm going to write it like this. 2 times 5 minus 2 times 3a minus 4 times a minus 4 times 7 equals 92. Okay, what did I do there? I used the distributive property. And I know what you're thinking. Some of you are saying, well, I wouldn't have done it that way. I would have said 2 times 5 is 10, and I would have just written 10. But hold on. There's another step that you're taking in there that I need you to be aware of. See, 2 times 5 is 10. So in my next step, I'll write that. What am I doing? If I know this expression equals 10, I can substitute 10 in for that expression anytime I need to. I'm using the substitution property, okay? So when you guys are solving a problem like this, if you distributed and you wrote 10 minus 6a, then essentially you've done two things. You use the distributive property and you substitute it at the same time, okay? So let's go ahead and do that for the rest of this equation. Negative 2 times 3a is negative 6a, and we have negative 4a, and then negative 4 times 7 is negative 28. Good, equals 92. Okay, what we did to get from this step to this step is we used the substitution property of equality. Okay, excellent. Now, what would we do next? I know some of you are saying, combine like terms. On the left side of that equation, that expression can be simplified. Let's go ahead and combine like terms. 10 and negative 28 give me negative 18, right? And negative 6a minus 4a gives me negative 10a equals 92. What did I do here? 10 minus 28 is negative 18, so I can substitute negative 18 in for that expression where I need to. Same thing with negative 6a minus 4a. Since it equals negative 10a, let's substitute it in. So we're using that substitution property again. Good. Now, I'm going to add 18 to both sides, right? If I want to continue to solve for a. So I'm going to write it like this. Negative 18 minus 10a plus 18 equals 92 plus 18. And yeah, I'm really trying to show you guys how much you rely on these properties and how much you often skip steps when you're solving equations. Not that there's anything wrong with that when you get really comfortable solving equations, but when you're doing a proof, you're justifying every step you take. So negative 18, first of all, what property did we use to get from here to here? We added 18 to both sides, so that is our addition property of equality, right? And hopefully some of you are catching on and you're seeing that negative 18 plus 18 equals 0, right? Made you look. And if it equals 0, can I go ahead and substitute 0 in for it? Negative 10a equals, and 92 plus 18 equals 110. Good. What did we do there? Since negative 18 plus 18 equals 0, I substituted 0 in for it. And since 92 plus 18 equals 110, I substituted 110 in for it. Good. Now, excuse me, I'm going to divide both sides by negative 10. So I'm going to say negative 10a divided by negative 10 equals 110 divided by negative 10. What did I do to go from here to here? I used our division property of equality. Okay? Good. And since negative 10 divided by negative 10 equals 1, I can substitute 1 in for it. And rather than writing 1a, I'm just going to write a. That's conventional, right? And 110 divided by negative 10 gives me negative 11. Okay? So we used our substitution property of equality. And did we arrive at our answer? Did we solve for a? Yes, we did. There's our first algebraic proof, okay? And as you guys can see, hopefully, you know how to do them. You've been doing them for a long time. You just haven't stopped to justify every statement that you've made. That's the proof process. Okay, here's a good summary of the proof process. Step 1, we want to list the given information and, if possible, draw a diagram to illustrate this information. In geometric proofs, you're frequently going to draw diagrams to help you through the proof process. In fact, the diagram becomes extremely helpful because sometimes you can visually see your way to the end of the proof, whereas you would not necessarily be able to figure out which direction to go next if you were simply writing down statements or reasons. So the diagrams are very important. That should come as no surprise in geometry. Another thing that we should be mindful of is list the given information. Now, sometimes you're asked to do a proof and it comes in this format. If a bunch of information, comma, then something must be true, okay? You'll see a lot of problems, a lot of proofs in this format. Hopefully this looks familiar to you. It is, of course, a conditional statement. And the words that come after the word if are hypothesis, right? If hypothesis, then conclusion, okay? So if you're seeing a proof in this format, then the given information is the hypothesis. That's the bit that comes after the word if, okay? And then step 2, state the theorem or conjecture to be proven. What are they asking me to prove? That will be the conclusion. That will be the bit that comes after the word then, okay? So if you see your proof written in this format, then you want to recognize that this bit's the given, okay? I'll even write it under there. And this is what you're being asked to prove, okay? And now you're going to create a deductive argument, which deductive reasoning, of course, involves the use of theorems, postulates, and other things that we know to be true that have already been proven and we're comfortable using them, like Pythagorean theorem. We've used Pythagorean theorem enough. Hopefully you've seen it proven, and if you've seen it proven, you're comfortable with it, and you can use that as a reason anytime you need to. So we're going to create deductive arguments using those theorems that we know. And we're going to learn a lot more theorems in geometry. Geometry is full of them, okay? So we're going to create a deductive argument by forming a logical chain of statements linking the given to what you are trying to prove. And these statements are going to look like, we're going to have 2 columns, okay? Our statements are going to be made over here, and our reasons are going to be over here. This is where we're going to state our theorems and postulates and things that we know to be true. Justify each statement with a reason. That's what you're going to put over here. If you make a statement over here, it's got to have a reason, okay? And the very first statement you're going to make is you're going to restate all of the good stuff that they give you in the hypothesis and the given. You're going to restate it. And then what's your reason for that? Given, okay? And then once you have all the given information stated, from that point on, you can begin your proof where you get to venture out on your own, making your own statements as long as you can justify them. And if you've justified a statement, then you can use that. You can rely on that further down the road, perhaps in your next statement or maybe 5 statements on. Okay, so we're going to justify each of those statements with a reason. Our reasons can include, like we said, algebraic properties. When we did our first algebraic proof, that's what we did. Our reasons were algebraic properties. But we can also use postulates, theorems, or just definitions. Just definitions. When we get into chapter 6, we might do some proofs with parallelograms. And there's a fundamental definition of a parallelogram. You may make a statement and justify it by definition of a parallelogram. All right, and then finally, if you get to a point where your last statement, hopefully you get to your last statement, let's say we were asked to prove X, that would have been up top, okay? That's going to be like our compass, like our GPS, keeping our eyes on the goal, where we're headed. If you finally get to a last statement where you have stated X, and you've justified it with a reason, then you are done your proof, okay? And you can circle that, and you can write this fancy Latin abbreviation QED, quod erat demonstratum. Sounds like a Harry Potter spell, I know. But that basically says that which was to be demonstrated has been proven, okay? Let's try some of these, but as you're working on them, come back to this and refer to it so that you kind of get comfortable with this whole process. All right, let's try that for this problem here. Complete a proof of this conjecture. If the formula for the area of a trapezoid is area equals 1/2 times the sum of the bases times the height, then the height of the trapezoid is given by h equals 2 times the area over the sum of the bases. Okay, now hopefully you recognize the pattern right away. Do you see the conditional statement? If hypothesis, then conclusion. Okay, if given, then prove. Okay, so let's go ahead and restate what we're being asked to prove. They're asking us to prove what? Prove that the height of a trapezoid equals 2 times the area divided by the sum of the bases. Okay, let's go ahead and make some statements and some reasons. We can make any statement we want as long as we can back it up with sound mathematical properties, right? Okay, what's the first statement we're always going to make in a proof? We're going to restate the given. Okay, remember, if hypothesis, all of that information right after the word if is your hypothesis. That's your given information. So they start us out with area equals 1/2 times the sum of the bases times the height. What's our reason for that first statement? That is our given. Okay, so where do we go from here? Remember, I said this is your compass, this is your GPS, this is your dashboard, right? This keeps you focused on your goal. Okay, every now and then you might want to look up there and say, hold on, what am I doing this for? Where am I going? What am I doing next? Oh, I'm trying to prove H. Okay, I'm trying to prove H. I know what to do next now. I want to get H isolated. So what would we do to do that? First step, perhaps you might get rid of the 1/2 by multiplying both sides by 2, right? So you might say 2 times the area equals 1/2 times B1 plus B2 times H times 2, right? What did we do there? We used our multiplication property of equality. Okay, I'll just write multiplication property. And then you might recognize that 1/2 times 2 is just 1, right? So you might rewrite this as 2a equals b1 plus b2 times h. What did we do? We recognized that 2 times 1/2 is 1, so we substituted 1 in for it. We used our substitution property. Okay. Now, what am I going to do next? I want to get that h by itself, right? So I think I'm going to say that 2a divided by b1 plus b2 equals b1 plus b2 times h divided by b1 plus b2. Okay, what did I do there? I used our division property of equality. Okay, and I recognize that b1 plus b2 divided by b1 plus b2 just equals 1, right? So I'm going to rewrite this as 2 times the area over the sum of the bases equals, since that equals 1, I'm just going to substitute 1 in for it. I get h. Okay, I used a substitution. Okay, now have I arrived at my destination? Does this look exactly like what I was asked to prove? It looks pretty close, doesn't it? But to make it look exactly like that, I've got to flip it around and say h equals 2a over b1 plus b2. Can I do that? Can I justify that? Does that violate any laws of mathematics? I can do that. What's my reason? Which property is that? That is our symmetric property of equality, right? I can flip any equation around. If that's a true equation, I can flip it around and I still have a true equation. Okay. Does it look exactly like what we were asked to prove? Yes, it does. I'm going to circle that and I'm going to say QED. Done. All right. let's try our first geometric proof now, okay? If angle A is congruent to angle B, the measure of angle B equals 2 times the measure of angle C, and the measure of angle C equals 45, then the measure of angle A equals 90. Write a 2-column proof to verify this conjecture. Now, they give us this as well. You may not see this on every problem, okay? And that's why I've pointed out to you that it's very important to recognize this pattern, this if-then conditional statement. If hypothesis, then conclusion, okay? If given, then proof, okay? Okay, so this is our given information. This is what we're being asked to prove. If you're not given this, you're going to want to make sure that you always write right at the top, the very first thing you write, what are you being asked to prove? Prove that the measure of angle A equals 90, okay? Keep that at the top of your paper. Again, that is your compass, your GPS. Keeping you focused on your destination. What is your goal here, okay? So we're going to arrive at our goal through a series of statements and reasons, okay? And in this particular case, you might want to draw a sketch. I mean, based on all the given information, I might start by drawing angle C. I'm going to call this angle C. I'm going to say it's 45 degrees, okay? And they're telling me that angle B is 2 times the measure of angle C, okay? So I can already picture this. And call this angle B. I can just picture it as 2 times. I just kind of drew it as 2 angle C's, but I can picture this as being 90 degrees, right? Okay, that helps me. And then I also see that angle A is congruent to angle B. All right, well, and I think I know the measure of angle A. I think it's 90 degrees. Okay, now you can see visually when you draw this sketch, you can already kind of see what you're being asked to prove. Now all you got to do is navigate your way through this jungle of statements and reasons. And it's not as hard as it might look. Our first statement, of course, is going to be the given information. They tell us that angle A is congruent to angle B. And they tell us that the measure of angle B equals 2 times the measure of angle C. And they tell us that the measure of angle C equals 45 degrees. Okay, what's my reason for all of this? That is all given. Good. Okay, so what's the first statement I'm going to make to try to prove that the measure of angle A equals 90? Well, first thing I want to do, and we're going to talk a little bit more about this in the next 2 lessons, but this is an algebraic statement, right? And so is this. And I'm really comfortable with those. We've been working with those for a long time. I just showed you guys how to do algebraic proofs. But this is a geometric statement, right? It's a statement of congruence. That is not an equal symbol, okay? And there's a reason for it, okay? We're going to talk a little bit more about that, a lot more about it in chapter 4. But basically, congruence and equality are analogous, but they're not the same thing. So could I turn this into a statement of equality so that I can work in the realm of algebra where I'm very, very comfortable? And sometimes you may want to do this. You may want to convert from geometric statements to algebraic statements and vice versa. That's the first thing I want to do. The algebraic equivalent of this statement is the measure of angle A equals the measure of angle B. Why? Because that's our definition of congruence. Congruent angles have the same measure. So I'm going to say that is our definition of congruent angles. Now remember, in that proof process I showed you, one of the things you can use, theorems, postulates or definitions. Okay? If you know the definition of congruent angles, you can use that to convert from a statement, a geometric statement, to an algebraic statement. Now that we have that, we can add, subtract, multiply, and divide, and we're really happy, right? For one thing, I might say that the measure of angle A equals 2 times the measure of angle C. How do I justify that? Well, notice up here it was given the measure of angle B equals 2 times the measure of angle C. So can I substitute that in for the measure of angle B anywhere I want to? Absolutely, we can do that. That is our substitution property of equality. Okay? And now, what else could we do? Could I say that the measure of angle A equals 2 times 45 degrees? Because remember, they told us that the measure of angle C is 45. So can I substitute 45 in for the measure of angle C anywhere I need to? Absolutely. Same property, substitution. And then, can I say that the measure of angle A equals 90 degrees? Absolutely. What did I do here? Now be careful here. This is actually just the substitution property of equality, isn't it? I'm recognizing that 2 times 45 equals 90, and so I'm substituting 90 in for it. Just because they're multiplying there, just because in that expression was multiplication, doesn't mean it's the multiplication property of equality. Okay, that's when you multiply both sides of an equation by the same thing. But that's not what we did here. We simply simplified. Okay, we recognize that this equals 90, and so we substituted it in. Now, does this look exactly like what we were asked to prove? Yes, it does. We have completed our proof. We've arrived at our goal, and we can say QED, done. Okay, one last example here to kind of demonstrate this idea. Again, you may not be given this bit here where they summarize the given and prove for you. You may only be given an if-then statement. Okay, so if you see these, don't forget to look for that pattern. If, hypothesis, then conclusion. All right, and the hypothesis is, of course, the given, and the conclusion is what you're being asked to prove. So, to always rewrite what we're being asked to prove, that RS equals 12. Okay, we're going to get there via some statements and reasons. And reasons. Okay. And you might want to make a sketch here. Okay, doesn't hurt. If I've got A, B, and C, D, let's just draw those. Here's A, B. Okay. And here's C, D. And they're telling us that AB is congruent to CD. I'm going to go ahead and mark that. Okay. And they also tell us that CD is congruent to RS. So let's go ahead and draw on RS right here. And they tell us that CD is congruent to RS. Okay. And they tell us that AB is 12. Okay. Now, hopefully, the visual proof for you here is apparent, right? If AB is congruent to CD, well, then CD must be 12. And if CD is congruent to RS, then RS must be 12. You can visually feel comfortable with what you're being asked to prove. Can we now put it into some statements and justify it using all the properties that we know? What are our first statements going to be? Always restate the given information. They tell us that segment AB is congruent to segment CD. They tell us that segment CD is congruent to segment RS. And they tell us that the measure of segment AB is 12 units long. Okay? How do we know all of this? That is given. Okay. Where do we go from there? Well, we could use the substitution property of equality, right? If we had maybe some more algebraic statements. The only algebraic statement we have here is AB equals 12. But what about the fact that segment AB is congruent to segment CD? Doesn't that mean that AB equals CD, that they are the same length, that they have the same measure? And doesn't that mean that since segment CD is congruent to segment RS, that CD equals RS, those segments have the same measure? The reason here is our definition of congruent segments, okay? And now, I think I could say that if AB equals 12, then I could substitute in 12 for AB. I could say 12 equals CD, okay? I did a substitution. And I'll show you a quick shortcut in a second that you could use, substitution property. There's another property that we've already learned that maybe you remember, maybe you're already thinking about it. And if 12 equals CD, could I substitute 12 in for CD here and get 12 equals RS? Okay, another substitution. Was that what we were asked to prove? Well, kind of. I only have to do one more thing. I have to say RS equals 12. Okay, and that is our symmetric property of equality. Okay, and can I go ahead and say QED? Absolutely. Now, one thing you might have recognized is, hold on, Mr. Rogers, why use two substitutions when you could have said if AB equals CD and CD equals RS and AB equals 12, why couldn't I just go ahead and say RS equals 12 using the transitive property of equality? Yes, you could use that. Instead of using two substitutions, you can use that transitive property. All right, guys, I hope you found that helpful. I hope you feel less intimidated by proofs and more confident that you can tackle these. I'm looking forward to working on some of these problems with you in class. And our next two lessons, we're going to build up our confidence in geometric proofs by doing some segment proofs and some angle proofs. Thanks for watching, guys.